Hi everyone, my Delta 2 Max was 100% at 9 p.m. yesterday, while continuing consuming 20 to 24 watts running on camera. Now, 10 a.m. the next day, it's almost dead. Is that normal to get empty in 13 hours?
Yes, the answer is yes. And I'm going to explain to you exactly why that's happening and the best ways to fix it. So let's go ahead and get into the details and learn something new today. So this is actually a really common topic. It's one of those things I see all the time. And when I see something all the time, I usually want to make a video to address it so that I can help people with those kind of questions and concerns. I don't really feel like this fits into the Solar 101 class that I'm working on right now. So I'll do this as a one-off video. And I really do see this asked a lot in a lot of different ways. Let's start with being here at the computer and talking about what is happening and why. And then after that brief introduction, we're going to jump off of the computer and go out into the field, aka my house, and we'll show you like real life stuff. We'll get some meters out, we'll measure it, we'll show it, and I'll show you the alternatives and how you might fix this. So the issue is this: whether you have an all-in-one power station like the person who I just read their question, or you're someone who's using a Victron inverter or any inverter, they're taking that DC power from your batteries and they're converting it into AC power for you to use with your appliances. That conversion, there is an efficiency loss, so you're going to lose some power in that conversion no matter what. So it's already what we consider inefficient. And two, because the inverter has to be on and running to do that conversion, it's going to have what we call a parasitic draw or a vampire draw. It basically has a minimum running wattage of its own, meaning nothing at all plugged into the inverter. Just having the inverter turned on will indeed drain your battery. And therefore, using an inverter to run a small AC load, such as a fan or a camera, anything tiny, is the worst way to go about doing it, because you're going to have a relatively small load from your actual appliance. And very, very often you might have an even larger load than that just from the inverter. A little extra knowledge: generally speaking, the larger the inverter, the more that drain will be. The smaller the inverter, the less it will be. And the inverter has an efficiency curve. So the more that you're using it, the higher the utilization, the more efficient it will be. So you're also hurting yourself even worse when you're buying a large inverter or a large power station to run a small thing. So that's the problem. That's what's happening. How do you fix it? Well, oftentimes, most of these small things like a fan or a camera, they come with wall warts, things you plug into the wall, and then usually a barrel connector or some other connector on the other end. And what that's doing is it's converting the AC from the wall into DC power for the appliance. And if you're using DC power and you have a battery, which is DC power, then what you want to do is completely cut the inverter out of this path. You want to find a way to go directly from your battery to your appliance with the right amount of voltage. And this can be done in so many ways, ways I want to cover in more detail in a separate video. Specifically, I'm going to release that one, and I'm going to tag it something about photographers and videographers and how to save a lot of money. Because as a photographer and videographer, I spent so much money on gear that needs batteries, and those batteries are super expensive. And now with the invention of power supplies like this that are portable and affordable, I'm running my stuff off of these now instead of buying those expensive batteries. And I just wanted to get that out there as a PSA for a lot of people to save them a lot of money. So that video will be coming out separate. But yes, what's happening is we're running the inverter. It's draining the battery, even if with the small loads. It's just a bad idea. It's inefficient. So what you want to do is, if possible, go directly from the battery to the appliance. Most of these are going to have like a 12-volt accessory port for your car. So you can get 12 volts out of that. And if your appliance works on 12 volts or close to 12 volts, you might be good to go straight from there. What you might have to do, though, is either boost that voltage or lower the voltage. So we have boost converters and buck converters that will either boost voltage, make it higher, or lower it. And I've used those in several videos, including if you go check out the channel and look at the solar shed build. I was going directly from solar panels to fans with no battery and no inverter, just using a buck boost converter. But the other thing is that people are maybe not understanding is now a really smart option is that USB has evolved. Now we have USB-C power delivery, and a lot of these devices are coming with like 100 watt or even higher, 140 watt. And now we have up to, I think it's 240 watts on a USB-C port. And you can use that as your DC. So these are all going to go directly to the battery, and you do not have to turn the inverter on. And doing so will save you so much power, because that 20 watt drain will now truly be a 20 watt drain against the battery, and you don't have to worry about fighting the inverter for the power. So that's what you want to do. And if you're wondering, how am I going to do that with USB-C ports? Let's just go to good old Amazon. And I'm going to search like USB-C trigger cable. And I've actually bought, here's one I bought. I like this one. I'll put it in the link. I'll put a link in the video description. So this one's really cool because it goes from USB-C to a barrel connector, but you can see it includes all of the adapters. So you can ensure that you find the right size barrel connector for your device, but it is actually an adjustable voltage. So unlike some of the other trigger cables that are, this one's only 5 volts, this one's only 12 volts, this one's only 20. This one offers many, many options, and you can set that voltage to whatever you need. And the other reason I liked this one specifically is as I was reading through, it actually had a pretty high current throughput, which is something else to keep in mind. When you're doing the buck and the boost, remember you're changing the voltage, but power isn't free. Energy cannot be created nor destroyed, only transferred. So if we're starting with 12 volts, for example, at say 1 amp, and you want to make that 24 volts, then in a perfect world, the best you could do would be 24 volts at half an amp for the same amount of power, aka wattage. But you're going to lose some of that power from the conversion. So that's why you have to be careful when you're picking your supplies out. What you might do for a mistake is say, ooh, this has the right voltage I need. Like in this case, here you go, 20 volts, 5 amps. That's 100 watts. That's really good. What if this only did 20 watts at 2 amps, but your device needed like 60 watts of power? Then it wouldn't be sufficient. So that's why you want to make sure you understand that power relationship. So USB cables are great. 12 volt socket accessories are great. And you can go a lot further than that. You can do more crazy stuff like look for a buck boost converter or something like that. And you'll find a whole bunch of them. So again, this is one that I've bought and I've used because I'm always tinkering around. So this will do 22 amps, and it was very effective. This is the one that we used in the solar shed actually to run the fans. That's the gist of this video. Let's go ahead and hop off the computer and go show you some real world stuff. All right, so for this I need to be hands-free, so forgive the fact that action cameras are not the best quality, but it's the content that's important. So I got a really nice high precision amp clamp meter here that does AC and DC. And what I wanted to show you, this is a Victron low frequency inverter, which means it's actually extremely efficient. So whatever losses I'm about to measure from here are going to be actually way worse for your standard power stations and your larger inverters. And again, like I said, the size matters. We have only 1,200 watts here at 48 volts. This is not a very large inverter. So this is one of the most efficient inverters I've ever seen, but it still has losses, and that's what we'll show you. So right now, let's go clamp on. We'll do the math on the computer in just a minute. But you can see 0.02, like it's just picking up basically nothing. It's just residual. And now we're going to kick on the inverter. And we're going to see that climb up. So absolutely no load on this, right? 0.2, we'll just round. We'll say 0.25 amps. We'll go back to the computer and do math in just a minute. So nothing connected to this. We're using 0.25 amps. We need to know what voltage that's at to figure out our wattage. That's pretty easy. I mean, we can look up here. I have it in the power station. So let's go pick up one of the dashes with more information. For example, let's go to power. So 67, that's the amps right here. That's the solar side right there.
54 volts. So we're at 54 volts of power getting to that inverter. So we'll just keep that in mind. Now, let's put some kind of load on here. I'm going to use a Steam Deck. I know it supports USB power delivery protocols. And I have a little meter on this so we can see the differences. So let's plug this guy in. You see it's starting to charge. Let's go look at this first. We've jumped up to 1.2, 1.1, 1. We'll estimate an average of 1.1 amps is how much we're pulling through that. But how much are we pulling just from this? Right here, guys. Just the Steam Deck right now is using 37 watts. So it's using 14.8 volts, about 2.5 amps, giving us about 36, 37 watts of power. And then it's slowly starting to calculate our watt hours. So with all those figures in mind, we can now jump back over to the computer and determine how much energy we're losing by using the inverter to do this instead of going directly from the batteries. That's what I did with the dashboard. USB goes to a DC to DC converter, which is going to be buck, not boost, but buck. It accepts 8 volts to 85 volts, and it drops it down to 5 volt, 3 amp on the output side. So this dashboard runs directly off the batteries, and it doesn't require any AC power. So as long as I have solar power and battery power, this will always run. And this inverter never gets turned on for anything except for emergencies.
Okay, so I just went through and I scrubbed and got all of our data to save us some time, and I already did the math so we can just talk about it. So with the Victron 48-1200, first of all, I said 1,200 watts. And Victron's a little bit different. They actually rate in volt amps VA, so it's really similar but not the same. Just wanted to point that out. But that was not the point of the video. The real thing is, what are we losing? What's our vampire drain or our parasitic drain? How much energy are we losing because we're using AC to DC to run a small thing? So we know when it was off, we had 0 amps at 54 volts, which means that was using no power, 0 watts. Once we turned on the inverter with nothing connected, it was using about 0.25 amps at 54 volts, which means it's using 13.5 watts just to be turned on. I had to put asterisks that this is a Victron low frequency inverter. It's extremely efficient, and it has like a built-in eco mode. So it's still using 13.5 watts just being on. So I can promise you that if you're using your EcoFlow power station, your Anchor power station, your Blue Eddy power station, or if you're using a larger inverter, these numbers are going to be much greater than just the 13.5 watts. So this is actually a best case scenario. So now with the Steam Deck being plugged in and we started charging it, we remeasured at the inverter 1.1 amps. And of course, we're still at 54 volts. So that means we're using about 59.4 watts of power. And then we measured independently with a inline USB power meter what we were actually delivering to that device. And it was 2.5 amps at 14.8 volts. So we were using 37 watts of power at the device. So we know that we have a loss of 13.5 watts with nothing connected. And then if we actually calculate our differences, we know that we were consuming almost 60 watts, but we were only getting about 37 watts. So we were losing, 22 watts of power in this example, which I said is actually one of the better examples you're going to run into. If I could actually show you an EcoFlow unit or something like that, it would be worse, but I don't have a good way to clamp onto the battery meter and show you. So now take that information and multiply it by 24/7 use, like the example we started the video with. And you'll understand just how fast that will consume your power station battery, especially because these power stations have usually 1,000 watt hours, and the one in the example was a Delta 2 Max. So it has about a 2,000 watt hour battery. And if you take this loss, let's do math on that too. And we're actually in a really good place to do that because of the figures we're working with. So it's pretty simple to do a watt-hour calculation. We already have watts, so 22.4 watts is how much we're losing. And let's calculate a 24-hour period, because that's when most people are going to check this. They're going to start something when they go to bed or when they get up in the morning, and then they're going to check again the next day, 24 hours later. In 24 hours, 22.4 times 24, my mental math is not that good. 24 times 24, 537.6. So 537.6 watt hours, which is more than half of a 1,000 watt hour power station, which would be like your Eco Flow Delta 3 Plus. And this, again, best case scenario. So if this was double the vampire load, you're going to cut that time in half, or you would need double the capacity. So in the example of a 2,000 watt hour station with double the drain, it would be exactly the same figures. We would still be running out of capacity in the same amount of time. So that's what happens. How can we make it better? Let me go look through my gear in the garage. I think I have a device or two that I might be able to use to show you what happens if we go DC to DC. And we'll calculate our losses from DC to DC and see if there's a big savings there.
So I figured I would find something that would work. And actually, this is something I bought a while back. This is a 240 watt USB-C power delivery converter thingamajig that I bought with the plans of actually building my own EcoFlow Trail 300 DC or something with higher capacity for cheaper. So this will work pretty well. It has a DC input right here. It accepts anywhere from 12 to 28 volts. So I can't use the same battery bank because the voltage would fry it. But we'll hook this up to the power station and we'll do the same measurements. And I'll still use the Steam Deck so that way we get apples to apples comparisons. All right, so forgive the mess. This should have been done, the big battery build that I was going to do this weekend. But we went to Busch Gardens. Some friends took us out, and one of the rides just like completely took me out. I had extreme vertigo all weekend, and I couldn't even get off the couch. So I'm hoping to get that done very soon. But this video is shorter and really important, so I wanted to squeeze it in. The setup is essentially the same. It's just we can't use the battery as the source now because the battery's voltage would fry this little USB adapter. This has a maximum of 28 volts. So what I did was I set 25 volts and 10 amps as our maximum from here. We can still measure it with the amp clamp meter, but we also get the fact all the data will be right in front of us. And we're going to remeasure this and see what happens. So I'm going to go ahead and kick it on. And you can see the vampire drain for this DC to DC device, if it's not broken, is 0. There's nothing. So no 12.5 or whatever. Let's go ahead and plug in the Steam Deck and see if it works. Stay. And we already plugged it in. Yeah, it's working because you see the Steam Deck's charging. All right. Let's get this all positioned in a safe manner. What a mess. Come on. There we go. Boom. All right. 38 to 39 watts coming out. 1.5 amps. Let's verify how accurate our meter was. So we should see about 1.5 amps. There we go, perfectly accurate. So the meter's good. We don't need it anymore since we get the specs from there on this side, but let's test it over here. The meter over here says 14.8 volts, 2.3 amps, 34.5 watts, 36.5 watts. We're only losing about 1.5 to 2 watts of power now with this DC to DC conversion. So you see how dramatic of a difference that is. So that's your goal. Anything that can run on DC, you want to run on DC. And when it comes to your power stations, you have the 12 volt accessory ports, you have the USB ports. And if you watch my channel, I often release hacks so that you can get direct access to the batteries, which gives you even more options. So this is what you want to shoot for. The next time you see someone asking this question or confused about what's happening, send them this video. That's the whole point of making these videos. I'm not trying to make money on it. I'm trying to share knowledge and fix all this misinformation in the world. So please help me accomplish that. Thank you again for watching, and I'll see you in the next videos.